So there is a reminder here. Does each researcher decide on his or her own alpha level? The answer is certainly not. Yes, there are three common alpha level that is introduced here, but you have to take note that per program or per area of specialization, there is like a convention already that is applied as to which level of significance is accepted. Now, in the field of psychology, psychologists agree that the appropriate level of significance that is tolerable in the field of psychology is 5% level of significance or alpha. In the field of medicine, which this is more crucial because the impact of committing error, because the alpha here is actually the risk you're taking that you might commit an error in your statistical analysis. So you cannot afford to have that bigger chance of committing error, 5%. Because take note, it would, it would compromise lives. Example, you're talking about medicine. Then you use 5% level of significance. And then later on, we found out that that is not actually significant just because you use this alpha value. So it turns out that it might cost lives, which the field of medicine cannot afford to do so. Okay, so that's why in the area of like those who are into researches for cure medicine, more or less 1% level of significance is the only tolerable risk. But in the field of psychology and most other fields as well, 5% is already accepted and became the conventional alpha value. So in every test analysis, your goal, if you intend to have a significant result, make sure your target is that your alpha value should be greater than your p value, or also known as the computed value. Okay, the p value, that's the computed probability value. Okay, I think we're good with this one. And by the way, you have to also remember that there are several tests that is applicable. Now, this one was the z-test. Since our probability distribution or the p-value was taken from our z-table. So that is because this is z-test. In the event that you're taking your probability value from t-table, then you are conducting a t-test. And then there is also f-tests or f-table. The f-table is intended, if I'm not mistaken, that is for the ANOVA, test of an analysis of variances. Okay, so in this case, we are using z-test as our p-value was taken from the z-table. There is a notation here. If your calculated z comes out to be 22, you can just say that the p is less than. Okay, there is here another. Remember, our z score is mostly from the z table. Okay, take note of this. Our z table, more or less, is up until 3.34. That's the best that we can accommodate. Because in the z table, at least the one that I uploaded, you can only look for the probability distribution equivalent to a z-score of 3.4. But what about if your z value is z equals 22? Now, if it's equals to 22, that's already very, very far. That's very, very small already, smaller than the alpha. So, reporting it twice, how do you report the result? Because, of course, you have to get the p-value. Our p-value here earlier was like, what was the p-value earlier? Oh, wait, I forgot the p-value of this example, 1.5, that is 4332. 0.5 minus 4 minus 4.4332. Okay, the p-value for this one here was 0.0635, 68 rather. Now that is 1.5. In the event that your z equals 22, you know that your z table will no longer accommodate. That's because you don't have this one. So how do we report the p-value for that? Our p-value should be reported as, okay, so instead of saying that p equals, our p-value equals certain portion, but since it's no longer found on the table, you can just say p value is less than, or rather, the p-value is less than 0.0001. Now, we cannot put it that the p-value is 0.00000, because if you put it all together 0, it means to say that it seems that there's nothing there. But the fact, or the fact of the matter is still there, that we cannot make it 0 because there is still, towards infinity, there is still a value there for, but that is just very, very small, very, very small compared to our alpha value. That's why, just to make it, just to have a reflection, or as to give an answer to this one, it is just equivalent to, we will just say now that if our z score is 20, or can no longer be found in the table, then we will just report our score to be p-value is less than 0.000. So assumingly, if this is your p-value, automatically, this is already less than our alpha, which is 0.05. Okay? So at least when this is our result, when the p-value is less than 0.0001 compared to our alpha, if the alpha was set to be 5% level of significance, then our decision is we reject the null hypothesis, coming up with a interpretation that our test is significant. You would think that it's really possible to have a z-score equivalent to 22, but this is likely impossible to happen when this will occur. Then probably there is something wrong with our sampling distribution, or there's something wrong with our sampling technique, sampling size, for example. Okay, this is still a possible result, but of course, you might encounter this one only when there is anomaly in your data, at least in the sample. Now, there is what we call here errors. I have here three null distribution. For the first null distribution, example, this is our alpha is 10%. So that means to say this is 10%, or that is 0.1. While the acceptance, or the confidence level here, the acceptance region is equivalent to 90%. If our alpha is, for example, our alpha is 0.05, that is how confident we are that at this level we can still reject the null hypothesis. Our confidence level here is increasing, and would increase also to 95%. Take note. If our alpha here is 1%, that's the alpha, then our confidence level is 99%. Now you notice, as you make your alpha smaller, then the confidence level becomes bigger and bigger. Now, the psychology is actually in this area here category, because the accepted, convention-wise, the accepted alpha value for psychologists is 5% alpha. While the field of medicine, most of them, at least their alpha value is, or the conventional alpha value is 1%. And then the 90%, which is not very much used but still possible, is this one. Now you notice, as we increase the alpha, as we decrease, we make the alpha smaller and smaller, the confidence level increasing. Now, in the event, example, here, the p-value is less than alpha, reject HO. That's our decision. So when the p-value is less than alpha, then reject HO. So in this case, as we reject HO here, what if, by any chance, due to um, undeniable circumstances, you happen to reject the null hypothesis, but actually you should have accepted it. So minus all the factors affecting it, you just happen to reject something which should be which supposedly accepted. So you rejected HO, but the event, I mean the event was you're supposed to accept it, supposed to accept HO. This would yield to the so-called type 1 error. Okay? You are committing type 1 error. So it's like, what type of error are you committing when you rejected the null hypothesis? It means to say you're committing a type 1 error. Type 1 error occurs when you rejected the null hypothesis when you're supposed to accept it. Now, if the p-value otherwise is greater than the alpha, it means to say you accept the null. Remember, the decision here is with accept HO. But in the event, what if you accepted the HO when it is supposed to be rejected? That's the opposite. So in that case, this would yield to a type 2 error. Actually, well, in this case here, you are most likely going to commit a type 1 error. Why type 1 error? It's because in this situation, you notice our alpha here is 10%. The risk of committing an error is 10%. So there is a greater chance of rejecting the null hypothesis. There is a greater chance of rejecting the null hypothesis. It's because there is a bigger region on which the p-value could fall into, resulting to rejecting the null hypothesis. Thus, as you reject the null hypothesis when it is supposed to be true, is type 1 error. Okay? Consequently, if we are in this case here, then most likely you are going to commit also a type 2 error. Because the tendency here is that there is a very small chance of rejecting the null hypothesis. And yet, in this scenario situation here, most likely you will commit a type 2 error. In this case, there is a greater risk of accepting the null, right? It's okay. There's a greater risk of accepting the null. It's because the confidence level is already 99%. And then the event that you accepted the null when it is supposed to be rejected is a type 2 error. Okay? So making the alpha smaller as possible would increase the chance of committing type 2 error. Increasing the alpha, giving a bigger room for rejection instead of room for accepting the alpha will most likely lead you to a type 1 error. Type 2 errors can be quite serious. So in those cases, we might want to use larger alpha. Consider the case of the researcher testing a cure for a terminal disease. So there is a researcher who is trying to do testing for a cure for a terminal disease. A type 2 error in this case would mean accepting the null hypothesis and failing to say that a particular cure has some effect, when in fact the cure does have some effect. But the researcher is too conscious to say so. In such a case, the researcher might consider using an alpha of 0.1 instead of 0.5. So it's like this. So the researcher is so conscious that instead of committing type 2 error, so he increases the alpha value, increases to a higher alpha values, let's say 10%, because he's too conscious of committing type 2 error. Type 2 error is actually accepting the null when the null is false. So, because of that consciousness, too much of being too conscious, he failed to recognize, or he might fail the chance of getting a result that the cure is statistically significant in coming up with an effect to a treatment. So, but because the researcher is too conscious of not committing an error, a type 2 error, that's why he misses that chance of finding a significant result. So there is always a confidence, there is always a consequence. That's why what the researcher could have done is that he must have make the alpha value to 1%. Okay, because in that case 1% it would give a smaller chance of committing type 2 error, which is accepting the null hypothesis when it is false. Because remember, when you're at 1% alpha, there is only 1% chance of accepting the null hypothesis. So there's a smaller chance of committing type 2 error. Okay? That is at least the case. We are moving to the point of the tailed tests. Okay, we have the one-tailed test and the two-tailed test. It's like this. Example, in an experiment or in your analysis of data, you anticipated, example, this is your in a diagram. You anticipated to reject the null hypothesis here at z-score of the mean of the sample group is supposed to be found at this one, 1.5. And then the result of the z-score or the mean of the sample group happens to be negative 1.5. So, but you anticipated to reject it here, but the rejection happens to be on this side, you cannot move further anymore. You can no longer proceed and say that to test any statistical significance on your tests. It's because you failed to anticipate area of rejection that is found in this area. So it's like saying now that you anticipated to reject it here when the result points you towards this direction. Consequently, with that, you can no longer move forward unless, if from the start, you started and then you anticipated to have both sides of rejection. Because if you have both sides of rejection, that means to say, if in the long run of the computation, you anticipated here and anticipated here, wherever is your rejection area in the process of rejecting your null hypothesis, you can still move forward. It's because you have both sides of rejection. This is an example of two-tailed. So convenience-wise, it is better to use two-tailed test. It's because in the event that you fail to anticipate where is the rejection region of your null hypothesis, so you can still move forward because you anticipated two directions. It could be there or it could be here. But if you certain and you decided to reject your null in this area, okay, you're certain that I'm going to reject or I'll be able to reject the null hypothesis on this side. And then in the process, the result yields the opposite, or the rejection yields, or the rejection region yields towards the opposite direction it was here. So you can no longer move forward. Statistically, you cannot say anything whether the test is statistically significant or not. It's because it's like you fail to anticipate the area of rejection, okay, where you could reject the null hypothesis. Now, this is an example of one-tailed test. Okay, there is two-tailed test and one-tailed test. So one-tailed test is actually anticipating a specific direction where you can reject the null hypothesis, while the two-tailed test is trying to anticipate two rejection area of your test analysis. It could be left or right of your mean. So when do we have a null hypothesis? When do we have a two-tailed test and one-tailed test? Actually, using your hypothesis, null and then alternative. For example, if your null hypothesis is, example, mean of the sample group is equal to 0, or equal to 0, that means to say the mean of your sample group is just exactly the same with your population mean. If the alternative, which is your claim, the mean of your sample group is not equal to 0, not equal to 0 implies non-directional. Non-directional means to say you do not specifically identify whether the mean of the sample group is greater than the mean of the population, or the mean of the sample group is less than the mean of the population. We're not saying there's no specific direction. Consequently, if this is the case, then there are any, at least in an illustration like this, we're anticipating two rejection area. That side, this side. But if your analysis or your statement is like this, HO is not equal to zero, meaning to say there is no difference with the mean of the population in the sample group. And then the alternative is there is, or the mean of the sample group is greater than the mean of the population, then that means to say that's one-sided, directional. Meaning to say you anticipated to reject null hypothesis on the right side of the right side of your mean of the population. Or you can also state it as mean of the sample group is less than zero, meaning to say you intend to reject the null hypothesis on this side. So these are what we call directional. Directional hypothesis. And then this is the non-directional. Literally, this one do not specify a certain direction where to reject the null, while this one has a specific direction where to reject the null. Now, the risk of doing this one is that you intend to have the alternative in this way. And what happened in the long run or in the process, the rejection found to be this one. So you cannot move forward. You cannot make any certain decision at all. It's because you fail to predict the right direction. But the good thing about the non-directional is that it gives you opportunity. Like for example, you haven't anticipated where to reject the null hypothesis. If it was rejected, or it is rejected here on the left side of your mean, it's possible because you have a rejection area here. If it will be rejected in this direction, it's also good because you still have a rejection area on this side of our distribution. Okay, but the problem here in the non-directional, it would increase or minimize of the chance of rejecting the null hypothesis because in this case we're not decreasing. If you notice in the two-tailed test, yes, assumingly it is conventional in the sense that it is convenient in the sense that either way you have your rejection area. That's good. But the problem is you're not decreasing here your confidence level. Remember the confidence level where you will accept the null hypothesis. You're not reducing the area to reject the null, the area to accept the null hypothesis. In fact, if your alpha here is 5%, your acceptance region in two-tailed test is still 95. What happened is your probability of rejecting the null hypothesis will be split into two because they are already two-tailed. So if your null hypothesis or your alpha level is 5%, that must be divided into two, equally divided, and then that will be distributed to the first side and then the second side. So example, if your alpha is 0.05, that is divided by 2, that will give you 0.025. This is 0.025. That's the side of the rejection. That's 2.5%, while the other one is 0.025. So you notice in one tailed test, there's a bigger room of rejecting the null hypothesis because this is right away 5%. Okay, the chance of rejecting the null hypothesis is bigger than this one. But this is more risky in the sense that what if the rejection falls on this side? You can no longer move forward. You cannot make any decision at all. It's because you failed to anticipate where you could have rejected the null hypothesis. On the other hand, there is also doing a two-tailed test is that the good thing about this one, you can anticipate whether it's on the right side or left side of your null hypothesis. There is both rejection area. But the problem is you're making the chance of rejecting the null hypothesis very small compared to this one. It's because your 5% alpha was already subdivided into two equal alphas. Two equal proportion, which is the right and the left side of your two-tailed tests. Okay, so that's also the risk, or at least that is the price of doing this one. But conventionally, what is normally suggested is the two-tailed test. Okay, because take note of the confidence. It is the same. Okay, that The acceptance region is still 95%, the alpha is 5%, but since the alpha was subdivided into two parts, which makes each part to be 2.5%. So that is making the chance of rejecting the null hypothesis very smaller, smaller than one-tailed test. But of course, this is safer in the sense that if this one doesn't have, there's nowhere else to go in rejecting the null hypothesis. But because if the null hypothesis is meant to be rejected in a certain alpha value, then this is all good because left or right, you have both rejection area. Unlike this one, there is a greater chance of rejecting the null hypothesis because it's solid 5% alpha. But the problem is, what if the rejection happens to be on the other side? Then that's also the risk. So there's always a risk on both sides. But what's suggested, highly suggested, is that you do a two-tailed. For a one-tailed test, example, this is 1.5. For a one-tailed test, and then the p-value is 0.06685. 0.6685. Got that. Okay. If this is the case, it is in one tail test at 5% level of significance, is this going to be accepted or rejected? Now let's look at this one. If this is 1.5, then looking at our table, 1.5 is this area here is 0.4332. So that means to say the area of rejection here, the probability here is, what's that? 0.5 minus 0.4332. This is 0.0668. So at this level here, at one tail test, in that area, if the p-value is this one, we can reject HO. Take note of that. Okay, because our contention here is that the p-value is less than or equal to your alpha, or at least to the p-value of the rejection region. Now, if in the event that we will use two-tailed test, now the two-tailed test will be like this. You will split now the two here. So I'm looking at this one, if this is 1.5, so what is this area? And at the same time, the area here and here are just the same. So looking at the table, so this is no longer 1.5. I'm assuming this is 0.025. We will look at the table. 0.05, that's 95. So 45, that's 47.5. This area here is 0.47. Okay? 0.475. That's 47.50%. At the same time, this area also is 0.475. Now, if that's the case, the probability of rejecting the null hypothesis, the p-value is this one, 0.025%. So if we look at this one, compare this value to this one, which is greater, 0.025 or 0.0668? This is greater than this one. Now, if you look at this one, this value is already found somewhere here. It belongs to the 0.475. So it means to say, if in this case, rejecting the null is our decision, in two-tailed test, we fail. We fail to reject. You notice we fail to reject because in this case, our p-value now is greater than our is greater now the probability distribution to the right of our z-score, to the right of our alpha. So in this situation, our alpha of 0.25, that's the rejection area of the distribution to the right, the p-value is greater than the alpha. Thus, we fail to reject null hypothesis. But in the one-tailed test, this is accepted. Okay, so I mean, that is more or less the situation now in doing a two-tailed test. So there is a significant difference in the decision once doing a one-tailed test or two-tailed tests. Okay, you should anticipate that. There are some reminders here that to remember. And number one, to perform a one sample experiment, select a random sample of some population that interests you, or select a sample from the general population and subject it to some experimental condition. Calculate the mean of the sample for the variable of interest and compare it to the mean of the general population. So, in doing a one sample experiment is that from the general population or from the population, you randomly select a sample from that population and then compute the mean of your sample and then compare the mean of your sample and the mean of the population. Okay, that's what is at least you're going to do in performing a one sample experiment or a one sample test. Even if the sample mean is different from the population mean in the direction you predicted, this result could be due to chance of fluctuation and random sampling. That is, the null hypothesis could be true. So if you look at this one, in the event that the sample mean, okay, this is the population mean and sample mean. If you compare the sample mean and then there's a difference between the two means, the population and the sample mean, then it is more or less attributed by the chances of fluctuation in random sampling. Maybe there is something, there is going on with the how you randomize your sample. Not logical enough to represent the population. No wonder that their means are not the same. That would attribute and result to a null hypothesis to be true. Okay, you get the point? If this is the mean of the population and the mean of the sample, if the means are not the same, then it is attributed perhaps with uh, misguided sampling or inappropriate sample size. These are the factors attributing to the changes of this one. Now, as a result of that, it would yield to a test hypothesis that would let you accept the null hypothesis. Okay? So so more or less, if that's the case, due to fluctuation of your sampling, it would ripple to an error that is called a type 1 error. That means to say, type 2 error. That means to say, you accepted the null hypothesis, making the null hypothesis to be true when it is supposed to be false. That is due to fluctuation of sampling. That's why from the very beginning, you have to emphasize very well sampling technique. The random, how you selected the sample is very important. How you select the sample is very important. It should be randomly, giving equal chances for everybody to be selected because it's a violation, and biases will occur when that is not if it doesn't say, it doesn't happen. And then another thing is that your sample size must be logical enough to represent the population, because more likely the chance of fluctuation in your sampling or fluctuation in the result, it is due to an illogical number of samples. Okay, example, the population is this big and then your sample is very much small compared to the population, plus the fluctuation of the sampling technique. The tendency is that it would create or it would yield to a test hypothesis that is equivalent to insignificant, which is from the first place, it could have been anticipated if your sampling technique as well as your sample size is done appropriately. Next, the null hypothesis distribution is a map. So your null hypothesis distribution, this one is like your map of what results are or are not likely by chance. For the one sample case, the null hypothesis distribution is the sampling distribution for the mean. Now, for one sample test, the null distribution is actually the distribution of the means, okay, of the sampling distribution. Because in a larger, like I said earlier, the beginning of our discussion, in a bigger group, you can come up with random samples. Take out samples, plural. So that means to say, some group 1, group 2, group 3, group 4, until how many groups you're going to come up. And then get the mean of each group, and then illustrate that one in your map, which is the null distribution, and locate the mean of each group in relation to the mean of the population. Okay? The mean of each group is, you're going to identify now how far that mean it deviates away from the mean of the population. And then from thereby, you can test the hypothesis whether there is a chance of rejecting the null hypothesis or not in relation to this population. That is how at least one sample test is done. Next, when the p-value for your experiment is less than the alpha, this is the decision. Take note of the decision. So if the p-value, okay, the probability value is less than the alpha, our decision is we reject the null hypothesis. Meaning to say, your claim is statistically significant. But in the event that, in that case also, you are most likely taking a risk of committing type 1 error, rejecting the null hypothesis when it is supposed to be true. On the other hand, when your p-value or your probability value is greater than the alpha, then that means to say you accept the null hypothesis. Accepting null hypothesis implies that there is no sufficient evidence yet to reject the null hypothesis. In that case, we are most likely there is a greater risk of committing a type 2 error wherein we accepted the null hypothesis when it is supposed to be rejected. And then third, if you make alpha small to reduce the proportion of type 1 errors, you will increase the proportion of type 2 errors. So it's balanced. If you increase your alpha, meaning to say you make your alpha smaller because you don't like to commit a type 1 error, you're also making a greater risk of committing type 2 error. And vice versa. If you also try to avoid committing type 2 error, then you are also increasing the risk of committing type 1 error. Okay, that is the reality for the test. One-tailed hypothesis tests make it easier to reach statistical significance. Okay, it's easier to reach statistical significance because your rejection area is clustered only in one direction. So like I said earlier, 5% of rejection, the proportion of rejecting the null hypothesis is there's a bigger chance of rejecting the null hypothesis compared to 2.5% of rejecting the null hypothesis. But again, the catch is that if you will use the one-tailed test and then you fail to anticipate and then the rejection happens to be on the other side, reverse on the other side, then you're nothing but helpless to continue. Okay, that's also the risk. If the calculated z for an experiment equals 1.5, so our calculated z is 1.07, example, that is the calculated z. Let us find the corresponding one-tailed p-value. What is the corresponding one-tailed and two-tailed value? Okay, so this is our case. Now let's make our map, our diagram, as to where we can locate this one. Let's start with the one tail first. Now we assign the value that is z equals 1.07. What is the probability now, or what is the probability value now if our z score is 1.07? So at this case, since we're using one tail test, so this is just one direction. This is just the direction here. What is our p-value? Now what we're going to do is we will look for the probability of this side here so we can get the p-value on this side. Looking at the z table, this area here, the one that I shaded horizontally, can you look for the probability distribution allocated for the z-score of this one using the z table? What is the probability distribution from the mean up until the sample mean of equivalent to a z-score of 1.07. What is the probability distribution? One, you look for 1.07 from the z-table, and then let's get this one so we can identify our p-value for one-tailed if our z-score is 1.07. This is for this area. Now, our concern is this one, the complement. So that's it, 0.50 or 0.5 minus 0.3577. Our answer is, we have 1423. 0.1423. So the p-value now for a z-score that is 1.07 under one tailed test is 0.1423. Okay? Now, for two-tailed tests, what will happen is like this. There are two rejection area. This is negative 1.07 and then this is positive 1.07 because there are two regions already that is inclusive of the positive and the negative, meaning to say above and below the mean. So the rejection area here is 0.1423, correct? Because that's the same with this one. And then this is 0.1423. Now, since we're looking for what is the corresponding two-tailed and two-tailed value, we're just going to combine this on 0.1423 plus 0.1423 is equal to 2.2846. 0. Let's find the two-tailed and one-tailed. For alpha equals, so for example, the alpha is 0.00005. Example, this is our alpha. What is the p-value now if this is our alpha? So we will do this one. We're looking for the z-score, okay? Our alpha is 0.005. Take note, since the alpha is 2.005, let's start with one tail. For one tail, that's just one area here. And then this is 0.005%. So that means to say that it's only this area here is 0.4995, correct? 49.5, and this is 0.005 times 100, 0.5%. So what we're going to do now is to get the z here, the z value, we're going to locate now on our table. What is the z value equivalent to the probability distribution of a z-score that is 0.495? What is the z-score? 49.5. Remember, we will get the closest z-score, but not the closest that is before, rather than the closest that is after. So in our case here, we have 0.4949, and we also have 0.4951. The closest that we're going to consider that is before 0.4995 is the 0.4949, which is 2.57. So our z-score is 2.57. So if our alpha is 0.005, in one tail test, the z-score equivalent to this alpha is 2.57. What about if it's two tail? So let's have the two tail. For the two tail, so what we're going to do now, we will divide the alpha into 2. So that's 0.005 divided by 2. That's already very small. 0.123. 2.5. Okay, the table can no longer accommodate us, but rather 1, 2, 3. That's 25. So if we will round it to two decimal places, that is 0.0003. If that's the case, so that is 0.005 minus, okay, let's consider the whole decimal place value, 0.00025 0.5 minus 0.0003025. The answer is 0.49997. 0.49975. So since our table here is only up to 4 decimal places, we can round up the decimal value to the nearest 4 decimal places. So that's 0.4998 because 7 then 0.75. So 4998. What is the z-score equivalent to 0.4998? 49. Now we have 09 for 4948, that is 34, 3.4. 3.49. 3.49. So our z-score here is 3.49 positive, and then the other one is negative 3.49 negative. So this is our z-score. Happening now when we have our alpha equivalent to 0.005, when we have two-tailed, our z-score is the positive and the negative 3.49, and then the one-tailed is positive 2.57. So there is really a difference.